Hi, welcome back to educator.com. Today we're going to talk about the 5-number summary and box plots. So now that you know a little bit about variability, now we could talk about the 5-number summary. And the box plot is going to be a way of just visualizing that 5-number summary just really quickly. And then we're going to talk about how to determine outliers, and we're going to be using conditional formatting in Excel. And finally, we're just going to talk about modified box plots, which are going to be box plots where we exclude the outliers already. All right, so there's really 2 ways to summarize a distribution. We've been talking about one way so far, where we talk about shape, center, and spread. And usually when we talk about shape, center, and spread, we often use as a measure of center mean. Right? So mean is what we really sometimes mean by center. It could be median, but a lot of times people use mean. And when we use spread, we often mean standard deviation rather than other pairs such as median and interquartile range, right? That's sort of where the 5-number summary comes in. The 5-number summary is a way of using the median and the interquartile range more as our measure of exactly as a summary of how our distribution looks. And so the 5 numbers are numbers you already know. The minimum value, the Q1, the border of the first quartile, the median, which is actually Q2, right? The median is also Q2 in that it divides the entire distribution in half, so 2 quartiles on one side, 2 quartiles on the other side. Also Q3, the third border, and then the maximum value, the highest value in your distribution. This 5-number summary is often used with skewed distributions. So let me just show you visually what this looks like. So let's say we have a whole bunch of just different data points. And here's our maximum value. I'll just put in a few more. So even. All right. So here's our distribution so far. Now, the 5-number summary would basically say the minimum value is important, the maximum value is important, whatever the value in the middle is, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, so about 6 or 7. So let's say something like that. The median, right? And then Q1 and Q3, which would be dividing sort of this by half, right? So around there. And also dividing this by half, which would be right there, right? So here's min, Q1, Q2, also the median, Q3, and also maximum, right? And so in that way, we get a 5-number summary. We may not know all the little dots in our distribution, but we have a very general idea of it. So now we're going to talk about a way to just visualize that 5-number summary just really quickly. It's going to be called a box plot. It's also called a box and whiskers plot. It's called box and whiskers because oftentimes there's a box, right? It could also be on its side, like this, with whiskers on it, right? And oftentimes this box is split up somewhere in between, not necessarily just in the middle, but just somewhere like that, right? This box is often aligned with an axis of values of your variable, right? And then your Q1 is on the low end, right? So Q1 is on the low end. Q3 is on the high end. Those are the sort of boundaries of that box. The line in the middle is the median. And the whiskers end at the minimum value and the maximum value. Okay? So that's how you decipher a box plot. Now, it could also be on its side like this, right? And in this case, the values would go like this. And once again, you would have Q1, Q3, the median, the minimum, and the maximum, right? And so it sort of doesn't matter whether it's on this axis or this axis, but what you do have to know is the box should be in alignment with the values, right? All right, so let's do an example box plot here just by hand, right? Here's an example set. We can easily see what the minimum and the maximum is, so we already know that. Let's find out what the median is. So the median should be right here, so that should be 30, right? Because what I'm going to do is add 28 and 32 and divide by 2. Just find the average of those two numbers, and that's 30. And visually, I just think of it as what's in the middle of 28 and 32. And then let's find Q1 and Q3. So what's in between here and here? That's 20. Wait. Oh, it should be, actually, I miscounted. Let's see. All right, so we count the 18 as the border, the 30 as the border, so each side gets sort of 2. So the Q1 is right in here, so that should be 22. And here, 30 is the border, 55, so it should be right here. Here's Q3. And that should be about 36.5. Is that right? About 1.5 from there, 1.5 from there. Okay. So there we go. We have our 5 numbers. Now we just need to plot them. I'm going to put it on a horizontal axis, just because I have the room for it. And I know that 18 will be on one side of it and 55 will be on the other side of it. So here I'll put my values. We could pretend this stands for age, then I would label it age, right? And let's see, maybe I'll start from 0, right? And sort of divide this up into tens, right? So 10, 20, 30, 40, 50, 60. Great. So let's start plotting our box and whiskers. What I like to start to do is just put dots there and then draw in the box and whiskers. So here I'd put in a dot where one of my whiskers is going to end. And here's the other end of that. And Q1 is right here about. 30 is right here, the median, and 36.5 is about right here. All right, and so now I know where my boundaries are, I could just draw my box and whiskers. And to help myself, I might just write down where Q1 and Q3 is, because that's going to help me draw my box. And here's my median, right? Here's my minimum whisker. Here's my maximum whisker. So this would be a box and whisker plot or a box plot for this data set that we have right here. Now let's talk about when box plots are actually useful. The pros of box plots is that you could plot a single quantitative variable and you could compare 2 or more distributions really easily. In fact, box plots are really useful for comparing lots of distributions very quickly because it's a good visualization, it's very compact, you could put it all on one graph, and it's easy to compare the boxes. When distributions have many, many values, too many to show individually, you wouldn't want to use a stem plot or a dot plot. You'd want to use something like a box plot. Also, it's nice when you don't need to see anything more than a 5-number summary. But one of the cons is that you can't see frequency accurately. For instance, you can't see how many people have the height of 72, right? But you can see a frequency within a range. You know that 50% of the people lie in between, Q1 and Q3, and you could see that really easily on a box plot. Now, how do we determine whether we have outliers in our data set? Well, outliers are simply extreme values, but that's a really subjective way of defining it. How do we know how extreme? Who defines extreme, right? Well, we have a rule of thumb in statistics. Typically, we determine outliers by saying that an outlier is 1.5 times the interquartile range from the nearest quartile, right? So what we really mean is the upper limit is the nearest quartile is Q3, and you add 1.5 times the interquartile range, whatever that is, right? So that's sort of the upper limit boundary. The lower limit boundary would be from the Q1 boundary, and because we're going lower, we're subtracting 1.5 times the interquartile range. Sometimes with skewed distributions, where the 5-number summary is really useful, you might not need one of these because one side might not have outliers, only the other side does. So if it's right skewed, we'd only have an upper limit boundary. If it's left skewed, we might only have a lower limit boundary. Now let's go on to some examples. So approximately what percentage of values in the data set lie within the box, right? So that box with those whiskers, right? What percentage of the data lie in there? Well, we know that this is 25% of our sample, as well as this is also 25%. And each of these quartiles are also 25%. So we know that what's in here is 50% of our sample. In the lower whisker, 25%, and the upper whisker, 25%. And that's one of the reasons why box plots are so useful. They just break up that data really easily into chunks that we could really use. So example 2, how would a box plot look for a data set that is skewed right? Now remember, in a skewed right distribution, we have a few of these outliers that are very, very great. They're very positive, way far away from, the negative side. So what would a box plot look like? Well, for a data set that's skewed right, which I'll write in red, skewed right. If we had a box plot that looked like this, we know that the right side, right whisker would be much longer than the left side, right? And probably also the right box would be longer than the left box. When it's up and down, remember that this side, the top part is the greater side, so it would just be this little picture, but just sort of spun around. So let me make this a little shorter. So here, this is the sort of negative end and positive end. This upper side is longer than the lower side. Now what about those populations that are skewed left? In that case, smaller numbers, there's more outliers on the sort of the smaller end of the continuum. So skewed left. In a side-to-side box, it would be really easy to see because the left side would be longer than the right side. And probably even within the box, you'd have that kind of, the left box being bigger than the right box. But remember, when we draw it up and down, the bottom end this time would be longer than the top end. So here, that's the positive end, that's the negative sort of end. And this side box would also be longer as well, right? So skewed left distributions we know either look like this or like this. Skewed right distributions we know look like one of these. What about approximately normal distributions? Well, when you draw it on its side, you know that it has to be roughly symmetrical because it's approximately normal. So that part is easy. But another thing about normal distributions is that most of the values, 60%, are clustered sort of within that, within a sort of small space, and then within one standard deviation away from the mean on either side. And so we could probably guess that these little tails might actually be a little longer than the actual box. So that's sort of how it'd look. But it's roughly symmetrical, you could see. And it's pretty easy to draw that on its side as well, because it's a roughly symmetrical picture either way, right? Example 3. How can you estimate the IQR from a box plot? Well, the IQR is actually really easy to see on a box plot because whatever the box is, the bottom end of that is Q1 and the top end of that is Q3. That's really your IQR, right? And can you estimate the range? If so, how? Well, the range is actually your minimum and maximum values. So the sort of the length of that entire box and whisker shebang, that would be your range. So interquartile range and range is really easy to see on a box plot. Example 4. Is it possible for a box plot to be missing a whisker? If so, give an example. If not, explain why not. Well, let's think about this. We know that when it's skewed, let's say skewed right, we know that this side's whisker can be very small and this side's whisker can be very long. Now, what would it mean for it not to have a whisker at all? Well, one thing might be that you might have so many values that are exactly the same, so you can't quite split them up into whisker and box. For instance, let me give you an example of a data set that might do so. Let's say it's out of 8 values, 1, 2, 3, 4, 6, 7, 8. I just picked 8 because it's really easy to split into quartiles, right? What if all of the values in both quartile 1 and 2 are exactly the same, right? And then 1, 2, 3, 4, right? Then you couldn't have whiskers because it would be arbitrary why these zeros get whiskers and these zeros get to be in the box. You'd probably put them all on the same box, or this would be a very, very thin box. All right, so that's an example. Obviously, you could do it with the other side as well. So this might be an example of a left skewed distribution that doesn't have a whisker. So something like 4, 4, 4, 3, all right? And then 1, 0, -1, -2, right? So in these kinds of plots, it's hard to say what the interquartile range would be. I mean, not the interquartile one. It would be difficult to arbitrarily say, well, 4 is the boundary for the whisker as well as the box, right? I mean, it can't be both, right? So these are the kinds of distributions that would be missing a whisker. So that's the end of box and whisker plots. Thanks for using educator.com.